All right, so let's continue with our week 3 discussions, okay? And we will continue here with equilibrium points, and linearization for non-autonomous or forced systems. Okay, so these are systems with input. Okay. Now the generalization is that we have now x dot is equal to a nonlinear function, often a vector function, of both a set of states and a set of inputs. Okay. For now, we will assume u is a scalar, but everything that we discussed can be very easily generalized. Okay. Now let's make a definition of an equilibrium point for such a system. Okay. Point. Okay. So a point in x bar, which is a vector again, in Rn is called an equilibrium point. We can also sometimes call this the equilibrium state. If there is a fixed specific input, now u is element of R, u bar again. Now this one is in this case called an equilibrium input. Such that this function f(x) u at that point and at that input is identically equal to 0. Remember, this 0 is also actually a vector, right? Because f is a vector function. Therefore, this equality is also a vector equality. Okay? Right? Hold on. I don't know why I can't progress in my notes. Okay, sorry. My tablet somehow started behaving strangely. So let's take a look at our pendulum example. So pendulum now with torque input. Okay, so a pendulum which has a motor in the center and which drives the pendulum. Okay, so our system is x1 dot is equal to x2, and as we have initially derived it, okay, x2 dot is equal to now the torque input tau over j, and our remaining terms mgl over j sine x1 minus b over j x2. Okay, now for using the above definition for equilibrium, we need to have, first of all, x2 needs to be identically 0. Okay, so our equilibrium state, or the equilibrium point, will have this term, the second state, being identically zero, and we need to also have this second equation equated to zero that needs to be satisfied. So for a equilibrium input tau bar, this equation needs to be satisfied. mgl over j sine x1. And because we know x2 is necessarily equal to 0 at equilibrium, we can just omit the last term. So, but this at this equilibrium point, x1 bar needs to satisfy this equation. Okay, so we need to have essentially like pairs. So x1 bar 0 equilibrium state and equilibrium input pairs satisfying the above equation. Okay, so this equation needs to be satisfied. Now, what does that mean? That means that we have a dependence at the equilibrium point. We have a dependence between the inputs and the state. Okay, so for a given equilibrium state, you need to find the corresponding equilibrium input, and for a given equilibrium input, you need to find the corresponding equilibrium state. Okay, if you can solve this equation, that is, which implies the presence of an equilibrium point. Okay, so let me express it this way for reference. Okay, for a given tau bar, we can find equilibrium points, which by that I mean equilibrium states, or for a given or desired, by the way, both of them can be interpreted as desired. In this case, you see, I always have a pair because sine function is generating two solutions. Okay, for a given equilibrium state, okay, or in this case states, because we have two of them, we can find tau bar, the input that, or let me call this, we can find the equilibrium input tau bar by satisfying the above equation. Okay, now how about linearization? Okay, how about linearization? That means finding the linear approximation to this nonlinear function around a chosen equilibrium. First of all, remember that we now have a function of both the state and the input. Therefore, this approximation takes the form of, first you evaluate this function at the equilibrium point and the equilibrium input, and plus you consider the Jacobian with respect to the state and multiplied by x minus x bar being the equilibrium state, plus, since you now also have a dependence with respect to the input, you also need to consider how this function changes with respect to the input as well. So we need to also take the derivatives with respect to input and apply, essentially multiply with the deviation from this input. Okay, remember I'm indicating u as a vector here as well, but in our case we will just consider a scalar input to simplify things a bit. So in the subsequent equation I'm going to consider u as so u is in our example here. Okay, so fx, the Jacobian with respect to the states, is as usual df1 over dx1, df1 over dxn, up to dfn over dx1 and dfn over dxn. Okay. This needs to be evaluated at x is equal to x bar, the equilibrium state, but also you need to evaluate at u is equal to u bar, because these terms, because f1 to fn will also be a function of u, so can be the derivatives. Okay. Similarly, the Jacobian with respect to u will look like, for a scalar input, df1 over du and up to dfn over du. And if obviously u is not a scalar, then this is not going to be a column vector, but it's going to become itself a matrix. So this one also needs to be evaluated at the same equilibrium state and the equilibrium input. Okay. So in this case, because we are evaluating everything at the equilibrium points, so what we obtain basically x dot is equal to f of xu will be approximately equal to, okay, simply f evaluated at the equilibrium point and the equilibrium input plus fx x minus x bar fu u minus u bar, and in this case this is going to be equal to 0 because of approximating around the equilibrium point and input. Okay, so this is essentially a linear approximation to the original nonlinear system around the equilibrium point and equilibrium input, to be specific. Okay, let me wrap this up with an example. It's the same example as we considered before, but slightly modified to have an input. So here is our example. So I will consider the nonlinear function or the nonlinear system where x1 dot is equal to x2 plus u times x1. So there is an input dependence now. And the second state derivative is the same as before. So minus x1 plus x1 cubed. No u dependence on that equation. Okay. So first find the equilibrium points. Okay. So the first thing is that since there is an equation without any u involved, let's first solve that. So minus x1 plus x1 cubed is equal to 0. So x1 times x1 square minus 1 is equal to 0. So that will give us simply x1 bar is equal to 0, another one x1 bar is equal to 1, and another one x1 bar is equal to minus 1. So three solutions from that equation for x1, the equilibrium, one component of the equilibrium state. Also, we need the first function also needs to be equal to 0. So I will need to also have x2 bar plus u bar times x1 bar is equal to 0. Okay, so this also needs to be satisfied at the equilibrium point. Okay, so one of the equilibrium points for x1 bar is equal to 0, we have necessarily, if x1 bar is equal to 0, x2 bar is also equal to 0. So that results x2 bar is equal to 0. And that gives us one of the equilibrium points, okay? X bar simply becomes 0, 0. And the input does not matter, okay? Input becomes becomes irrelevant. That means this point is an equilibrium point independent of the input. The input does not matter for this point, okay? But for other x1s, for example, if x1 bar is equal to 1, okay, now we have an x2 bar, and this becomes a function of the input, okay? So we have u is equal to minus x2 bar. U bar is equal to minus x2 bar. This is with any x2 bar. What does that mean? That means for x1 bar is equal to 1, we don't have a single equilibrium point, but we have a continuum of equilibrium points. Okay? It just depends on the input. Okay? Choose the input and you have an equilibrium point. Or choose the equilibrium point and you have an equilibrium choose the equilibrium point and you have an input, and choose the input and you have an equilibrium point. Okay? Now let me give you an example. For example, if you have, let's say, a one-dimensional, let's say, rotor system, like you have a motor and a propeller, and it just floats this bar in the air. What does that mean is that you can generate an equilibrium point anywhere by just adjusting the DC voltage of the propeller. Because if you increase the DC offset of the propeller, you will generate an equilibrium point higher over here, maybe. And then if you reduce the DC offset of the motor, you can generate another equilibrium point somewhere here. So that means you can actually generate an equilibrium point anywhere by simply adjusting the equilibrium input. And you can, as we will see, you can generate a linear approximation to this system anywhere. And for those of you who have taken 407 process control, this also coincides with what we call the operating point. Okay? By simply selecting an equilibrium input and an equilibrium state, you can generate an operating point around which you can linearize the system. And just to give you another example, this is also the case for a transistor circuit. Basically, what you do is you create a DC offset condition. That means you generate a DC bias, which is, in a sense, the equilibrium input. Okay, you create an equilibrium point around any chosen state. And then around that state, you can approximate the system as a linear system, and you can do all kinds of small signal amplification and things like that. All right. So similarly, let me also wrap this up with the third possibility, where we have x1 is equal to -1. In that case, again, we have an x2 bar, but this time the equilibrium input and equilibrium state relationship is different. In this case, they are equal to each other. So again, this is with any x2 bar. Okay. So let me give you, so these are the three equilibrium points. One of them is really a singular point. The other two of them are actually equilibrium conditions which can be satisfied with choosing the proper input and the proper state. Okay? Let me give you a numerical example from our system. So let's say that, for example, we choose x is equal to -1, 1, and we choose u is equal to 1. Okay, you see that it's an instance of the third case. Okay, we have -1 for the first state. The second one can be anything, but we have chosen it to be 1, and we have chosen the corresponding equilibrium input to be equal to 1, and therefore this is an equilibrium point. We can create infinitely many equilibrium points by choosing the input and the state according to this equation. Okay, now what I want to do is, what is the linear approximation of the system? Okay, how can I find the linear approximation to the nonlinear system around this chosen point? Okay, so let's do that. So we have z dot is equal to the Jacobian matrix. Remember, this is composed of, okay, let me remind you, df1 over dx1, df1 over dx2, df1, df1 over dx, this is dx2, right? So this one, so df2 over dx1, okay, sorry about the mess up. Okay, so this one is df2 over dx1, remember. So all the first row should be f1, all the second row should be f2, df2 over dx2. Okay, so here, for example, if we consider our equations over here, so this is our x1, so I take the derivative with respect to x1, this gives me u. And similarly, you take the same equation and you take the derivative with respect to x2, so you get 1. And similarly, you get 3x1 squared minus 1 over here and 0 over there. Okay? So remember, I need to evaluate this to x is equal to x bar and u is equal to u bar times z plus, again, remember what this is. This is df1 over du, df2 over du. Okay? So let's take a look. Here, df1 over du, I get x1 over here, x1, and similarly I get 0 over there. Okay, times this needs to be evaluated again at x is equal to x bar, u is equal to u bar, and times v, where v, where v is equal to u minus u bar, okay, by definition. So this is your new shifted input. Remember, again, for those of you taken 407, these we call the deviation variables, right? The deviation state and the deviation input. Okay? So what does that give me? Now I need to evaluate this, these two matrices at this chosen point. So if you put the values in there, what you will get is z dot is equal to 1, 1, 2, 0 times z plus minus 1, 0 times v. Okay, so this is our linear approximation. Now this is a linear system with an input, to our original forced nonlinear system around the chosen equilibrium point. Now I want to finish off with kind of a practical example. So let's say you have let's say a system with a motor and a propeller here, and you want to control this system, but you want to keep it at an angle of 30 degrees. Okay, so let's say task is to control system and stabilize it around theta is equal to 30 degrees. So what's going to be the approach to this kind of a problem? Let's think about everything that we learned. First of all, this is a nonlinear system, okay? Because you see there is a mass here, let's say m. So there will be mg, gravity here. There will most likely be a friction over here, okay? And here the input is not at the joint. It's not a torque input, but it's an input. It's a force generated by this propeller. Okay, so it's a system with an input. It's a nonlinear system with an input. So therefore, it just corresponds to everything that we have discussed here. Okay. So how can we approach designing a controller for such a system? Now, we need to find a linear approximation to the system. We need to find it around the angle that we want to control it around. So we need to first derive the nonlinear system of equations, the state space equations. We need to find the equilibrium conditions. Then we need to define we need to find the equilibrium input, which will give us an equilibrium state around the 30 degrees. Okay, so the equilibrium state where the angle is at 30 degrees. In that case, that will give us an equilibrium input, which will be essentially a force, a DC component of a force, the equilibrium force, that will basically keep this around this point. But this point is not a stable point. Any disturbance, it's gonna take us away from this point unless we actually design a controller for this system. Okay, and we can do that by finding the linear approximation to the system around exactly this operating point by the procedure that we have covered thus far. And then by using that linear state space system approximation, you can just design a controller for it. And in fact, this is going to be the kind of activity that you will be doing for your experiments in our course. Okay, so that concludes our topic of finding linear approximations to nonlinear systems including systems that are non-autonomous, systems with input, in a kind of a more formal setting than we were able to do in 407. And hopefully this is going to help you in being able to approach some of the later experiments that we have in the course. Okay, so see you guys later. That's going to be all for now.